So this is what your graphs should have looked like. So here's a normal action potential at the top, right? We know it's got the upstroke depolarization, the downstroke repolarization, and then the undershoot here, we get back to rest. Under the influence of TEA, because we block potassium channels, we're gonna see the upstroke unaffected, right? It's gonna go up perfectly fine. Those voltage gated sodium channels are still intact. But as far as the rapid repolarization, that is going to be influenced because potassium can no longer get out of the cell because of blocking these channels, then we don't repolarize effectively, right? And the membrane potential stays really high and then it kind of gradually comes down on its own. So repolarization is influenced under the effect or under the impact of tetraethylammonium toxin or TEA toxin. As far as TTX, this would be a completely flat line, right? The voltage gated sodium channels are really what initiate the action potential. And so if we block these, then the membrane potential does not change from rest. So a graph that reflects the TTX or the tetrodotoxin is going to remain unchanged at resting because we cannot initiate that upstroke or that depolarization, okay? So this is essentially what your graphs should have looked like under the influence of both of these toxins. And I'm sure we can start to imagine how these toxins are so lethal and so deadly, kind of similar to the toxins we looked at earlier. Because they impact the action potential, they're going to be extremely neurotoxic. They're going to cause paralysis, right? Muscles going to be paralyzed. Nerves are going to be paralyzed under the influence of these two toxins. Okay. All right. So any questions there about? Okay, so an excellent question. How is TEA able to eventually go downhill? And that's because of the leak channel. So remember, we still have leak channels for potassium, and the membrane is a lot more permeable to potassium. And so eventually over time, along with the action of the sodium potassium pump, we're gonna get that potassium out of the cell. It's not gonna be as rapid as if we had the movement through those voltage gated potassium channels, okay? So potassium will eventually leave the cell. The membrane potential will be restored mainly because of that sodium potassium pump, also because of the contribution of the leak channels. And so we can get back to rest. So getting back to rest is easier than depolarizing if we don't have sodium channels. If we don't have sodium channels, there's no way we're gonna leave rest, right? That's gonna be a more, think about it as a uphill event, or if you remember, we talked about spontaneous events versus active, active movement versus passive movement, uphill movements versus downhill movements. And so getting back to rest is gonna be a bit more spontaneous, it's gonna happen, but getting uphill or to start an action potential is impossible if we don't have those voltage gated sodium channels. All right, okay, that was a good question. Okay, so the last couple of things here are just looking at some practice questions. I'm going to share a poll and allow you to think about this question and then poll in an answer, and then we will discuss. Oops. It might be nice to actually launch the poll. I'm sorry. Okay, there we go. All right, let's take a look here. Okay, so an action potential either fires or not, all or none, and it maintains its strength as it travels. How does a graded potential compare? Majority of the response selected C, and C says it is weak depending on the stimulus strength and it dissipates away from the stimulus. So that is absolutely correct. We know that graded potentials are not all or none. So A is incorrect, B is incorrect. They are actually graded, right? There's gradation there. They can be small, medium, large. And then D says it is weak depending on the stimulus strength, but maintains its strength as it travels. And so the last part of D is incorrect. It actually dissipates, which we know from the point of the stimulus. Okay, so the correct answer here was C. Let's look at another one. Okay, final 10 seconds here. All right, let's take a look. Okay, so an action potential travels all the way down an axon. Where does a graded potential travel? So a lot of response for A, synapse, hillocks, and terminals. So that is not correct, okay? So there's a fundamental misunderstanding here. The correct answer is actually B, which is the second highest in terms of the responses. Dendrites, cell body, and sensory receptors. I was hoping no one would say D, but a few people did select D, which says nowhere that it does not travel. That's not true. We know it does travel because it dissipates as it travels. So D is incorrect. A is incorrect because it doesn't get to the terminals or the axon hillock. And then C is incorrect, again, because it doesn't get to the axon hillock or the actual axon. So B is the correct answer here. Graded potentials travel along the proximal part of the neuron, so along the dendrites, the soma or the cell body, as well as any sensory receptors on the proximal area of the neuron. It doesn't get past the axon hillock. At the axon hillock is where we determine if we have enough strength to fire an action potential. If we don't, by then it's dissipated. And if we do, at that point, it becomes an action potential and actually propagates down the axon, okay? So the correct answer here is B, dendrites, cell body, and sensory receptors. All right, I think we have two more, so oops. Okay, sorry about that. So let's look at this question here. All right, final couple seconds. Okay, so this question, what is the response of an action potential to a very strong stimulus? Majority of the response selected D, which is all of the above. That is not correct, okay? So essentially we know that the amplitude of an action potential cannot change, the duration of an action potential cannot change, and so that makes D incorrect as well. And what is the amplitude? The amplitude is the magnitude or the strength of the change. And so it never gets past positive 30. It's always from negative 70 to positive 30. So the value in terms of the strength there is always 100 millivolts in terms of that change. It can never get higher. It can never be smaller. It's always from negative 70 to positive 30, okay? So that's the amplitude of the action potential, doesn't change. Duration also doesn't change. The action potential is a little over a millisecond, 1 to 2 milliseconds. That duration never changes. That's why it's so important for this to be a timed event so it can start and stop at the exact same time always. Amplitude is always the same, duration is always the same. So in terms of the nervous system communicating a strong stimulus, the only way that we can do that is to increase the rate or the frequency. In other words, how fast those action potentials are being fired one after the other. So I can fire action potentials at a rate of maybe 10 in 1 minute. That's pretty slow. Or I can fire action potentials at a rate of maybe 100 in 1 minute, which is really fast. And that's going to be the difference between a strong stimulus, maybe a loud sound, again, if you're lifting something heavy. So this is how the nervous system creates gradations in terms of appreciating different stimuli by manipulating the rate or the frequency. In other words, how fast those action potentials are fired one after the other. But the quality of a single action potential never changes. The amplitude never changes. The duration never changes. So the correct answer here would have been B, okay? Very, very important. And then I think we have one more question. We'll try to squeeze this one in. So I'll give you a minute here and then we'll call it a day. Okay, so let's go ahead and take a look here. So during repolarization in an action potential, what happens to the membrane permeability of sodium and potassium? And we kind of touched on this. We talked about this before. Majority of the response selected B, permeability of potassium increases, permeability of sodium decreases. That is absolutely correct. And so that's what's responsible for the repolarization during the action potential. Okay, so that is all.